a real villain?
Well, technically, nah.
Have you ever caught a good guy like a real superhero?
Nah.
Have you ever tried a disguise?
Nah.
All right. I can see that I will have to teach you how to be villains.
If we're just dealing with two dimensions and we want to find the area under a curve, we have good tools in our toolkit already to do it. And I'll just remind us of our tools. So let's say that's x-axis, that's the y-axis. Let me draw some arbitrary function right here. That's my function f of x. And let's say we want to find the area between x is equal to a. So that's x equal to a, and x is equal to b. We saw this many videos ago, that the way you can think about it is you take super small widths of x, or super small changes in x. We could call them delta x's, but because they're so small, we're going to call them a dx. We're going to call them a dx. Super infinitesimally small changes in x. And then you multiply them times the value of f of x at that point. So you multiply it times the height at that point, which is the value of f of x. So you get f of x times each of these infinitesimally small bases. That'll give you the area of this infinitesimally narrow rectangle right there. And since each of these guys are infinitely small, you're going to have an infinite number of these rectangles in order to fill the space. You're going to have an infinite number of these, right? And so the tool we used was the definite integral. The definite integral is an infinite sum of these infinitely small areas, or these infinitely small rectangles. And the notations that we use would say we'd go from A to B. And we've done many videos on how do you evaluate these things. But I just want to remind you conceptually what this is saying. This is conceptually saying, let's take a small change in x, multiply it times the height at that point. So small change in x, multiply it times the height at that point. And you're going to have an infinite number of these, because these x's are super small. They're infinitely small. So you're going to have an infinite number of those. So take an infinite sum of all of those from x is equal to a to x is equal to b. And that's just our standard definite integral. Now what I want to do in this video is extend this, broaden this a little bit to solve I guess maybe you could say a harder or a broader class of problems. Let's say that let's go to 3 dimensions now. And I'll just draw the xy plane first. Maybe I'll keep this just to kind of make the analogy clear. So let me draw it. I'm going to kind of flatten this so we have some perspective. So let's say that this right here is the y-axis, kind of going behind the screen. As you can imagine, if I just pushed on this and knocked it down. So that's the y-axis, and that is my x-axis right there. That is my x-axis. And let's say I have some path in the xy plane. And in order to really define a path in the xy plane, I'll have to parameterize, I have trouble saying that, both the x and y variables. So let's say that x is equal to, let me switch colors. I'm using that orange too much. Let's say that x is equal to some function of some parameter t. And let's say y is equal to some other function of that same parameter t. And let's say we're going to have t go from t is going to be greater than or equal to a, and then less than or equal to b. Now this will define a path in the xy plane. And if this seems confusing, you might want to review the videos on parametric equations. But essentially, when t is equal to a, you're going to have x is equal to, so at t is equal to a, you're going to have x is equal to g of a, and you're going to have y is equal to h of a. So you're going to have this point right here. So maybe it might be, I don't know, I'll just draw an ordinary or random point here. Maybe that's when t is equal to a, you're going to plot the coordinate point g of a. That's going to be our x coordinate. This is g of a right here. And then our y coordinate is going to be h of a. Right? You just put t is equal to a in each of these equations, and then you get a value for x and y. So this coordinate right here would be h of a. And then you would keep incrementing t larger and larger until you get to b. But you're going to get a series of points that are going to look something like, let's say it looks something like that. That right there is a curve, or it's a path in the xy plane. And what you're saying, hey, how does that relate to that right now? What are we doing? Well, let me just write a C here for saying that's our curve or that's our path. Now, let's say I have another function that associates every point in the xy plane with some value. So let's say I have some function, f of xy. F of xy. What it does is it associates every point on the xy plane with some value. So let me plot f of xy. So let me make a vertical axis here. Let me do it in a different color. Call it the f of xy axis. Maybe we could even call it the z axis if you want to. But it's some vertical axis right there. And for every point, so if you give me an x and a y and you put into my f of xy function, it's going to give you some point. So I can just draw some type of a surface that f of xy represents. And this will all become a lot more concrete when I do some concrete examples. So let's say that f of xy looks something like this. I'm going to try my best to draw it. I'll do it a different color. Let's say f of xy, some surface. I'll draw part of it. It's some surface that looks, let's say it looks something like that. That is f of xy. F of xy. And remember, all this is you give me an x and you give me a y. You pop it into f of xy. It's going to give me some third value that we're going to plot in this vertical axis right here. Examples, f of xy. It could be, I'm not saying this is a particular case. It could be x plus y. It could be f of xy. These are just examples. It could be x times y. If x is 1, y is 2, f of xy will be 1 times 2. But let's say when you plot for every point on the xy plane, when you plot f of xy, you get this surface up here. And we want to do something interesting. We want to figure out not the area under this curve. This was very simple when we did it the first time. I want to find the area, if you imagine a curtain or a fence that goes along this curve this path. You can imagine this being a very straight linear path going just along the x-axis from A to B. Now we have this kind of crazy curvy path that's going along the xy plane. And you can imagine if you drew a wall or curtain or a fence that went straight up from this to my f of xy. So let me do my best effort to draw that. So let me draw it. So it's going to go up to there. And maybe this point corresponds to there. And when you draw that curtain up, it's going to intersect it something like that. Let's say it looks something like that. So if this point right here corresponds to that point right there. So if you imagine you have a curtain, you could f of xy is the roof, and this is what I've drawn here, this curve. This kind of shows you the bottom of a wall. This is some kind of crazy wall, and let me say this point, it corresponds to. Well, actually, let me draw it a little bit different. I want to draw it. This point will correspond to some point up here. So when you trace where it intersects, it'll look something like maybe like that. I don't know, something like that. And I'm trying my best to help you visualize this. So this side, maybe I'll shade this in to make it a little solid. Let's say f of xy is a little transparent. You can see, but then you have this curvy looking wall here. And the whole point of this video is how can we figure out the area of this curvy looking wall? Right? This curvy looking wall. That's essentially the wall or the fence that happens if you go from this curve and jump up and hit the ceiling at this f of xy. So let's think a little bit about how we can do it. Well, if we just use the analogy of what we did previously, we could say, well, look, let's call this, let's make a little change in distance of our curve. Let's call that ds. ds. That's a little change in distance of my curve right there. And if I multiply that change in distance of the curve times f of xy at that point, times f of xy at that point, I'm going to get the area. I am going to get the area of that little rectangle right there. Right? So if I take ds, my change in my, you can imagine the arc length of this curve at that point. So let me write, ds is equal to super small change in arc length of our path or of our curve. That's our ds. So you can imagine the area of that little rectangle right there along my curvy wall is going to be ds, I'll make it a capital S, ds times the height at that point. Well, that's f of xy. F of xy. And then if I take the sum, because these are infinitely narrow, these ds's are they have infinitely small width. If I were to take the infinite sum of all of those guys from t is equal to a to t is equal to b, right? From t is equal to a, I keep taking the sum of those rectangles to t is equal to b right there. That will give me my area. I'm just using the exact same logic as I did up there. And I'm not being very mathematically rigorous, but I want to give you the intuition of what we're doing. We're really kind of just bending the base of this thing to get a curvy wall instead of a straight, direct wall like we had up here. But you're saying, Sal, this is all abstract, and how can I even calculate something like this? This makes no sense to me. I have an s here, I have an x and a y, I have a t. What can I do with this? And let's see if we can make some headway. And I promise you, when we do it with a tangible problem, the end product of this video is going to be a little bit hairy to look at. But when we do it with an actual problem, it'll actually, I think, be very concrete, and you'll see it's not too hard to deal with. But let's see if we can get all of this in terms of t. So first of all, let's focus just on this ds. So let me re-pick up the xy axis. So if I were to reflip the xy, let me switch colors. It's just getting a little monotonous. So if I were to reflip the xy axis like that, I'm actually only doing that same green, so we're dealing with the same xy axis. So that's my y-axis. That is my x-axis. And so this path right here, if I were to just draw it straight up like this, it would look something like this. It would look something like this. Right? That's my path, my arc. This is when t is equal to a. So this is t is equal to a. This is t is equal to b. Same thing. I just kind of picked it back up so we can visualize it. And we say that we have some change in arc length. Let's say this. Let me switch colors. Let's say that this one right here. Let's say that's some small change in arc length, and we're calling that ds. Now, is there some way to relate ds to infinitely small changes in x or y? Well, if we think about it, and this is all a little bit hand wavy. I'm not being mathematically rigorous, but I think it'll give you the correct intuition. If you imagine you can figure out the length of ds if you know the lengths of these super small changes in x and super small changes in y. So if this distance right here is dx, infinitesimally small change in x. This distance right here is dy, infinitesimally small change in y, right? Then we can figure out ds from the Pythagorean theorem. You can say that ds is going to be, it's the hypotenuse of this triangle. It's equal to the square root of dx squared plus dy squared. So that seems to make things a little bit, we can get rid of the ds all of a sudden. So let's rewrite this little expression here using this sense of what ds. ds is really the square root of dx squared plus dy squared. And I'm not being very rigorous, and actually it's very hard to be rigorous with differentials, but intuitively I think it makes a lot of sense. So we can say that this integral, the area of this curvy curtain, is going to be the integral from t is equal to a to t is equal to b of f of x, y. Instead of writing ds, we can write this times the square root of dx squared plus dy squared. Now, we at least got rid of this big capital S, but we still haven't solved the problem of how do you solve something, an integral, a definite integral that looks like this. We have it in terms of t here, but we only have it in terms of x's and y's here. So we need to get everything in terms of t. Well, we know x and y are both functions of t, so we can actually rewrite it like this. We can rewrite it as from t is equal to a to t is equal to b. And f of xy, we can write it, f is a function of x, which is a function of t. And y is and f is also a function of y, which is also a function of t. So you give me a t, I'll be able to give you an x or a y. And once you give me an x or y, I can figure out what f is. So we have that. And then we have this part right here. I'll do it in orange. Square root of dx squared plus dy squared. But we still don't have things in terms of t. We need a dt someplace here in order to be able to evaluate this integral. And we'll see that in the next video when I do a concrete problem. But I really want to give you a sense for the end product, where the formula we're going to get at the end product of this video, where it comes from. So one thing we can do is, if we allow ourselves to algebraically manipulate differentials, what we could do is let us multiply and divide by dt. So one way to think about it, you could rewrite. So let me just take a do this orange part right here. Let's do a little side right here. So if you take this orange part and write it in pink, and you have dx squared, and then you have plus dy squared. And let's say we just multiply it times dt over dt. Right? That's a small change in t divided by a small change in t. That's 1. So of course you can multiply it by that. If we were to bring this part inside of the square root sign, right? So let me rewrite it this. This is the same thing as 1 over dt times the square root of dx squared plus dy squared, and then times that dt. Right? I just wanted to write it this way to show you I'm just multiplying by 1. And here I'm just taking this dt, writing it there, and leaving this over here. And now if I wanted to bring this into the square root sign, this is the same thing. This is equal to, and I'll do it very slowly just to make sure I'll allow you to believe that I'm not doing anything shady with the algebra. This is the same thing as the square root of 1 over dt squared. Let me make the radical a little bit bigger, times dx squared plus dy squared. And then all of that times dt, right? I didn't do anything. You could just take the square root of this, and you get 1 over dt. And then if I just distribute this, this is equal to the square root, and we have our dt out at the end, of dx squared, or we could even write dx over dt squared, plus dy over dt squared, right? Dx squared over dt squared is just dx over dt squared. Same thing with the y's. And now all of a sudden, this starts to look pretty interesting. Let's substitute this expression with this one. We said that these are equivalent. And I'll switch colors just for the sake of it. So we have the integral from t is equal to a. And let me get our drawing back. From t is equal to a to t is equal to b of f of x of t times, or f of x of t and and y of t. They're both functions of t. And now instead of this expression, we can write the square root of, well, what's dx? What's the change in x with respect to time, or whatever this parameter is? What is dx dt? Dx dt is the same thing. Dx dt, let me write this down. Dx dt is the same thing, actually I should write it here, is the same thing as g prime of t, right? X is a function of t. The function I wrote is g prime of t. And then this dy dt is the same thing as h prime of t. We could say that, this function of t. So I just want to make that clear. We know these two functions, so we can just take their derivatives with respect to t. But I'm just going to leave it in that form. So the square root, and we'd take the derivative of x with respect to t squared plus the derivative of y with respect to t squared, and then all of that times dt. And this might look like some strange and convoluted formula, but this is actually something that we know how to deal with. We've now simplified this strange, this arc length problem, or this line integral, right? That's essentially what we're doing. We're taking an integral over a curve or over a line, as opposed to just an interval on the x-axis. We've taken this strange line integral that's in terms of the arc length of the line and x's and y's, and we've put everything in terms of t. And I'm going to show you that in the next video, right? Everything is going to be expressed in terms of t, so this just turns into a simple definite integral. So hopefully that didn't confuse you too much. I think you're going to see in the next video that this right here is actually a very straightforward thing to implement. And just to remind you where it all came from, I think I got the parentheses right. This right here was just a change in our arc length. That whole thing right there was just a change in arc length, and this is just the height. This is just the height of our function at that point, and we're just summing it, doing an infinite sum of infinitely small lengths. So this was the change in our arc length times the height. This is going to have an infinitely narrow width, and you're going to take an infinite number of these rectangles to get the area of this entire fence, or this entire curtain. And that's what this definite integral will give us, and we'll actually apply it in the next video. The last video was very abstract in general, and I used, f of x and g of t and h of t. What I want to do in this video is do an actual example. So let's say I have f of xy. Let's say that f of xy is equal to xy. And let's say that we have a path in the xy plane, or a curve in the xy plane. I'm going to define my curve. Say my curve is going to be defined by x being equal to cosine of t and y being equal to sine of t. And we're going to go from, it's not, we have to define what are our boundaries on our t. And we're going to go from t is equal to 0, or t is going to be greater than or equal to 0, and then less than or equal to, we're going to deal in radians, pi over 2. If this was degrees, that would be 90 degrees. So that's our curve. And immediately, you might already know what this type of a curve looks like. And I'm going to draw that really fast right here. And then we'll try to visualize this. I've actually graphed it ahead of time so that we can visualize this. So this curve right here, if I were to just draw it in the standard xy plane, let me do that in a different color so we can make the curve green. So let's say that is y, and that this is right here x. So when t is equal to 0, x is going to be equal to cosine of 0. Cosine of 0 is 1. Y is going to be equal to sine of 0, which is 0. So t is equal to 0. We're going to be at x is equal to 1, right? That's cosine of 0. And y is sine of 0, or y is going to be 0. So we're going to be right there. That's at t is equal to 0. When t is equal to pi of 2, what's going to happen? Cosine of pi over 2, right? That's the angle. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we're going to be at the point 0, 1. So this is when we're at t is equal to pi over 2. And you might recognize what we're going to draw is actually the first quadrant of the unit circle. When t is equal to pi over 4, or 45 degrees, we're going to be at square root of 2, square root of 2. You can try it out for yourself, but we're just going to have a curve that looks like this. It's going to be the top right of a circle, of the unit circle. It's going to have radius 1. And we're going to go in that direction from t is equal to 0 to t is equal to pi over 2. That's what this curve looks like. But in the last video, our goal isn't here just to graph a parametric equation. What we want to do is raise a fence out of this kind of base and rise it to this surface. So let's see if we can do that, or at least visualize it first. And then we'll use the tools we used in the last video. So right here, I've graphed this function, and I've rotated a little bit so you can see the other case. This right here, let me get some dark colors out. That right there is the x-axis. That's the x-axis. That in the back is the y-axis, and the vertical axis is the z-axis. And this is actually 2. This is 1 right here. Y equals 1 is right there. So this is it graphed that way. So if I were to graph this contour on the xy plane, it would be under this graph, and it would go like something like this. Let me see if I can draw it. It would look something like this. This would be on the xy plane. This is the same exact graph. F of x is equal to xy. Let me make that clear. This is f of x. F of xy is equal to xy. That's both of these. I just rotated it. In this situation, this is now, that right there is now the x-axis. I rotated it to the left, you can kind of imagine. That right there is the x-axis. That right there is the y-axis. It was rotated closer to me. That's the z-axis. And then this curve, if I were to draw it in this rotation, is going to look like this. When t is equal to 0, we're at x is equal to 1, y is equal to 0. And it's going to form a unit circle, something like, or half or a quarter of a unit circle like that. And when t is equal to pi over 2, we're going to get there. And what we want to do is find the area of the curtain that's defined. So let's see, let's raise a curtain from this curve up to f of xy. So if we keep raising walls from this up to x of y, we're going to have a wall that looks something like that. We're going to have a wall that looks something like that. Let me shade it in, color it in, so it looks a little bit more substantive. So a wall that looks something like that. If I were to try to do it here, this would be under the ceiling, but the wall would look something like that, right there. We want to find the area of that. We want to find the area of this right here, where the base is defined by this curve, and then the ceiling is defined by this surface here, xy, which I graphed and I rotated into situations. Now, in the last video, we came up with well, you could argue whether it's simple, but the idea is, well, let's just take small arc lengths, change in arc lengths, and multiply them by the height. Multiply them by the height at that point. And those small change in arc lengths, we call them ds. And then the height is just f of xy at that point. And we'll take an infinite sum of these from t is equal to 0 to t equal to pi over 2. And then that should give us the area of this wall right there. So what we said is, well, to figure out the area of that, we're just going to take the integral from t is equal to 0 to t is equal to pi over 2. It doesn't make a lot of sense when I write it like this, of f of x y times, or let me even better, instead of writing f of xy, let me just write the actual function. Let's get a little bit more concrete. So f of xy is xy times, so the particular xy times the little change in our arc length at that point. And I'm going to be very hand wavy here. This is all a little bit of review of the last video. And we figured out in the last video, this change in arc length right here, this change in arc length, ds, we figured out that we could rewrite that as the square root of dx versus, or the derivative of x with respect to t squared plus the derivative of y with respect to t squared, and then all of that times dt. And so I'm just rebuilding the formula that we got in the last video. So this expression can be rewritten as the integral from t is equal to 0 to t is equal to pi over 2 times xy. But you know what? Right from the get-go, we want everything eventually to be in terms of t. So instead of writing x times y, let's substitute the parametric form. So instead of x, let's write cosine of t. So let me write cosine of t. Right? That is x. X is equal to cosine of t on this curve. Right? X, that's how we define x in terms of the parameter t. And then times y, which we're saying is sine of t. Times sine of t. That's our y. All I did is rewrote xy in terms of t, times ds. ds is this. It's the square root. It's the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared. All of that times dt. And now we just have to find these two derivatives. And it might seem really hard, but it's very easy for us to find the derivative of x with respect to t and the derivative of y with respect to t. I can do it right down here. We'll lose our graphs for a little bit. So we know that the derivative of x with respect to t is just going to be, what's the derivative of cosine of t? Well, that's minus sine of t. And the derivative of y with respect to t, derivative of y with respect to t, derivative of sine of anything is the cosine of that anything. So it's cosine of t. And we could substitute these back into this equation. So remember, we're just trying to find the area of this curtain that has our curve here as kind of its base and has this function, this surface, as its ceiling. So we go back down here, and let me rewrite this whole thing. So this becomes the integral from t is equal to 0 to t is equal to pi over 2. I don't like this color. Of cosine of t, sine of t, cosine times sine, that's just the xy, times ds, which is this expression right here. And now we can write this as, well, I'll go switch back to that color I don't like, the square root of, the derivative of x with respect to t is minus sine of t, minus sine of t, and we're going to square it, plus derivative of y with respect to t, that's cosine of t, and we're going to square it. Let me make my radical a little bit bigger. And then all of that times dt. Now, this still might seem like a really hard integral until you realize that this right here, when you take a negative number and you square it, this is the same thing. Let me rewrite. Let me do this in the side right here. Minus sine of t squared plus cosine of t squared. This is equivalent to, this is the same thing as sine of t squared plus cosine of t squared, right? You lose the sign information when you square something. It just becomes a positive. So these two things are equivalent. And this is the most basic trig identity. This comes straight out of the unit circle definition. Sine squared plus cosine squared, this is just equal to 1. So all this stuff under the radical sign is just equal to 1. And we're taking the square root of 1, which is just 1. So all of this stuff right here will just become, it'll just become 1. And so this whole crazy integral simplifies a good bit. It just equals the square root t equals 0 to t is equal to pi over 2 of, and I'm going to switch these around just because it'll make it a little easier in the next step, of sine of t times cosine of t, sine of t times cosine of t dt. All I did, this whole thing equals 1, got rid of it, and I just switched the order of that. It'll make the next step a little bit easier to explain. Now, this integral, you say, hey, sine times cosine, what's the antiderivative of that? And the first thing you should recognize is, hey, I have a function or an expression here, and I have its derivative. The derivative of sine is cosine of t. So you might be able to do u substitution in your head. It's a good skill to be able to do in your head, but I'll do it very explicitly here. So if you have something as derivative, you define that something is u. So you say u is equal to sine of t, and then du dt, the derivative of u with respect to t, is equal to cosine of t. Or if you multiply both sides by the differential dt, if we're not going to be too rigorous, you get du is equal to cosine of t dt. And notice, right here, I have a u, and then cosine of t dt, this thing right here, that thing is equal to d of u. And then we just have to redefine the boundaries. When t is equal to 0, so we're going to have, this thing is going to turn into the integral. Instead of t is equal to 0, when t is equal to 0, what is u equal to? Sine of 0 is 0. So this goes from u is equal to 0. When t is pi over 2, t is pi over 2, sine of pi over 2 is 1. So when t is pi over 2, u is equal to 1. So from u is equal to 0 to u is equal to 1. Just redid the boundaries in terms of u. And then we have, instead of sine of t, I'm going to write u. And instead of cosine of t dt, I'm just going to write du. And now this is a super easy integral in terms of u. This is just equal to, the antiderivative of u is u 1/2 times u squared, right? We just raised the exponent and then divided by that raised exponent. So 1/2 u squared, and we're going to evaluate it from 0 to 1. And so this is going to be equal to 1/2 times 1 squared minus 1/2 times 0 squared, which is equal to 1/2 times 1 minus 0, which is equal to 1/2. So we did all of that work, and we got a nice simple answer. The area of this curtain, we just performed a line integral. The area of this curtain along this curve right here is, that area, let me do it in a darker color, is 1/2. If this was in centimeters, it would be 1/2 centimeters squared. So I think that was, a pretty neat application of the line integral.
Now listen closely. Here's a little lesson in trickery. This is going down in history. If you want to be a villain member.
So let's say I have a function of x and y, f of x and y is equal to x plus y squared. If I try to draw that, let's see if I can have a good attempt at it. That is my y-axis. I'm going to do a little perspective here. This is my x-axis. I could make it do the negative x and y-axis. You could do in that direction. But this is my x-axis here. And if I were to graph this, when y is 0, it's going to be just a, let me draw it in yellow. It's going to be just a straight line that looks something like that. And then for any given x, you're going to have a parabola in y, right? Y is going to look something like, y is going to look like that. I'm just going to do it in the positive quadrant. It's going to look something like that, like that, like that. It'll actually, when you go into the negative y, you're going to see the other half of the parabola, but I'm not going to worry about it too much. So you're going to have this surface that looks something like that. Maybe I'll do another attempt at drawing it. But this is our ceiling we're going to deal with again. And then I'm going to have a path. I'm going to have a path in the xy plane. I'm going to start at the point, I'm going to start right there at the point 2, 0. X is equal to 2, y is 0. And I'm going to travel, just like we did in the last video, I'm going to travel along a circle, but this time the circle is going to have a radius 2. I'm going to go counterclockwise in that circle. This is on the xy plane, just to be able to visualize it properly. So this right here is the point 0, 2. Then I'm going to come back along the y-axis. This is my path. I'm going to come back along the y-axis, just like that. And then I'm going to so I took a left here, and then I'm going to take another left here, and then come back along the x-axis. I'm going to come back along the x-axis, right, like that. So this, what I drew in these two shades of green, that is my contour. And what I want to do is I want to evaluate the surface area of essentially this little building that has the roof of f of xy is equal to x plus y squared, and I want to find the surface area of its walls. So you'll have this wall right here, whose base is the x-axis. Then you're going to have this wall, which is along the curve. That's going to look something like, I don't know, it's going to look kind of a funky wall on that curved side right there. I'll try my best effort to actually it's going to be curving way up like that. So it's going to be curved up like that. And then along the y-axis, when x is equal to 0, it's going to have like a half of a parabolic wall right there. I'll do that back wall along the y-axis. I'll do that in orange. Actually, I was already using orange. I'll use magenta. That is the back wall along the y-axis. Then you have this front wall along the x-axis. And then you have this weird curvy curtain or wall. Do that maybe in blue. That goes along this curve right here, this part of a circle of radius 2. So hopefully you get that visualization. It's a little harder. I'm not using any graphic program this time. But I want to figure out the surface area, the combined surface area of these three walls. And in very simple notation, we could say, well, the surface area of those walls, of this wall plus that wall, is going to be equal to the line integral along this curve or along this contour, however you want to call it, of f of xy, so that's x plus y squared, ds, where ds is just a little length along our contour. And since this is a closed loop, we'll call this a closed line integral. And you'll sometimes see this notation right here. That notation, often you'll see that in physics books. And we'll be dealing with a lot more. You put a circle on that integral sign. And all that means is that the contour we're dealing with is a closed contour. We get back to where we started from. But how do we solve this thing? Well, a good place to start is to just define the contour itself. And just to simplify it, we're going to divide it into three pieces and essentially just do three separate line integrals. Because this isn't a very continuous contour. So the first part, let's do this first part of the curve where we're going along a circle of radius 2. And that's pretty easy to construct. If we have x is equal to, let me do that in each part of the contour in a different color. So if I do an orange, this part of the contour, if we say that x is equal to 2 cosine of t, and y is equal to 2 sine of t, and if we say that t, and this is really just building off just what we saw in the last video, if we say that t, and that this is from t is greater than or equal to 0 and is less than or equal to pi over 2, t is essentially going to be the angle that we're going along this circle right here. And this will actually describe this path. And if how I constructed this is a little confusing, you might want to review the video on parametric equations. So this is the first part of our path. So if we just wanted to find the surface area of that wall right there, we know we're going to have to find dx, dt, and dy, dt. So let's get that out of the way right now. So if we say dx dt is going to be equal to minus 2 sine of t, dy dt is going to be equal to 2 cosine of t. Just took the derivatives of these. We've seen that many times before. So if we want this orange wall's surface area, we can take the integral. And if any of this is confusing, there are two videos before this where we kind of derive this formula. But we could take the integral from t is equal to 0 to pi over 2 of our function of x plus y squared, and then times the ds times, so x plus y squared will give the height of each little block, and then we want to get the width of each little block, which is ds. But we know that we can rewrite ds as the square root, I'll give myself some room right here, of dx of the derivative of x with respect to t squared, so that is minus 2 sine of t squared, plus the derivative of y with respect to t squared, so plus 2 cosine of t squared dt. This will give us the orange section, and then we can worry about the other two walls. And so how can we simplify this? Well, this is going to be equal to, and I'll write over here, the integral from 0 to pi over 2 of x plus y squared. And actually, let me write everything in terms of t. In terms of t. So x is equal to 2 cosine of t. So let me write that down. So it's 2 cosine of t plus y, which is 2 sine of t, plus 2 sine of t. And we're going to square everything. And then all of that times this crazy radical. Right now it looks like a hard antiderivative or integral to solve, but I think we'll find out it's not too bad. This is going to be equal to 4 sine squared of t plus 4 cosine squared of t. We can factor a 4 out. Now we don't want to forget the dt. This over here, let me just simplify this expression so I don't have to keep rewriting it. That is the same thing as the square root of 4 times sine squared of t plus cosine squared of t. We know what that is. That's just 1. So this whole thing just simplifies to the square root of 4, which is just 2. So this whole thing simplifies to 2, which is nice for us solving our antiderivative. It simplifies things a lot. So this whole thing simplifies down to, I'll do it over here. Now I don't want to waste too much space. I have 2 more walls to figure out. The integral from t is equal to 0 to pi over 2. And I want to make it very clear. I just chose the simplest parameterization I could for x and y, but I could have picked other parameterizations, and I would have had to change t accordingly. So as long as you're consistent with how you do it, it should all work out. There isn't just one parameterization for this curve. It's kind of depending on how fast you want to go along the curve. But watch the parametric functions videos if you want a little bit more depth on that. But anyway, this thing simplifies. We have a 2 here, 2 times cosine of t. That's 4 cosine of t. And then here we have 2 sine squared sine of t squared. So that's 4 sine squared of t. So that's 4 sine squared of t. And then we have to multiply it times this 2 again. So that gives us an 8. 8 times sine squared of t dt. And then, sine squared of t, that looks like a tough thing to find the antiderivative for. But we can remember that sine squared of really anything, we could say sine squared of u is equal to 1/2 times 1 minus cosine of 2u. So we can reuse this identity. If I could write a t here. Sine squared of t is equal to 1/2 times 1 minus cosine of 2t. Let me rewrite it that way, because that'll make the integral a lot easier to solve. So we get the integral from 0 to pi over 2. And actually, I could break up, well, I won't break it up. A 4 cosine of t, 4 cosine of t, plus 8 times this thing, right? 8 times this thing. This is the same thing as sine squared of t. So 8 times this, 8 times 1/2 is 4. 4 times 1 minus cosine of 2t. Just use a little trig identity there. And all of that dt. Now this should be reasonably straightforward to get the antiderivative of. Let's just take it. The antiderivative of this is antiderivative of cosine of t. That's just sine of t, right? The derivative of sine is cosine. So this is going to be 4 sine of t. The scalars don't affect anything. And then, well, let me just distribute this 4. So this is 4 times 1, which is 4, minus 4 cosine of 2t. So the antiderivative of 4 is 4t plus 4t. And then the antiderivative of minus 4 cosine of 2t, let's see, it's going to be sine of 2t. Let's see, sine of 2t. Sine of 2t. The derivative of sine of 2t is 2 cosine of 2t. We're going to have a minus sign there and put a 2 there. And now it should work out. What's the derivative of minus 2 sine of t? Take the derivative of the inside. 2 times minus 2 is minus 4. And the derivative of sine of 2t with respect to 2t is cosine of 2t. So there we go. We figured out our antiderivative. Now we evaluate it from 0 to pi over 2. 0 to pi over 2. And what do we get? We get 4 sine of pi. Let me write this down. 4, I don't want to skip too many. Sine of pi over 2 plus 4 times pi over 2. That's just 2 pi minus 2 sine of 2 times pi over 2, sine of pi. And then all of that minus All of this evaluated at 0. And that's actually pretty straightforward, because sine of 0 is 0. 4 times 0 is 0. And sine of 2 times 0, that's also 0. So everything, the zeros work out nicely. And then what do we have here? Sine of pi over 2. In my head, I think sine of 90 degrees, same thing. That is 1. That is 1. And then sine of pi is 0. That's 180 degrees. So this whole thing cancels out. So we're left with 4 plus 2 pi. So just like that, we were able to figure out the area of this first curvy wall here. And frankly, that's the hardest part. Now let's figure out the area of this curve. And actually, you're going to find out that these other curves, since they go along the axes, are much, much, much easier. But we're going to have to find different parametrizations for this. So if we take this curve right here, let's do a parametrization for that. Actually, you know what? Let me continue this in the next video, because I realize my videos have been running a little long. But I'll do the next two walls, and then we'll sum them all up.
You have to chase a superhero on the run. Just follow my moves and sneak around. Be careful not to make a sound. No, don't touch that.
In the last video, we set out to figure out the surface area of the walls of this weird looking building, where the ceiling of the walls was defined by the function f of xy is equal to x plus y squared. And then the base of this building, or the contour of its walls, was defined by the path where we have a circle of radius 2 along here. Then we go down along the y-axis, and then we take another left, and we go along the x-axis, and that was our building. And in the last video, we figured out this first wall's surface area. In fact, you can think of it, our original problem is we wanted to figure out the line integral along the closed path. So it was a closed line integral along the closed path C of f of xy, and we're always multiplying f of xy times a little small distance of our path, ds. We're writing this in the most abstract way possible. And what we saw in the last video is the easiest way to do this is to break this up into multiple paths, or into multiple problems. So you can imagine this whole contour, this whole path we call C, but we could call this part that we figured out in the last video C1. This part we can call, let me make a pointer, C2. And then this point right here, C3. So we could redefine, or we can break up this line integral, this closed line integral, into 3 non-closed line integrals. This will be equal to the line integral along the path C1 of f of xy ds plus the line integral along C2 of f of xy ds plus the line integral, you might have guessed it, along C3 of f of xy ds. And in the last video, we got as far as figuring out this first part, this first curvy wall right here. Its surface area we figured out was 4 plus 2 pi. 4 plus 2 pi. Now we got to figure out the other two parts. So let's do C2. Let's do this line integral next. And in order to do it, we need to do another parametrization of x and y. It's going to be different than what we did for this part. We're no longer along this circle. We're just along the y-axis. So as long as we're there, x is definitely going to be equal to 0. So that's my parametrization. X is equal to 0. If we're along the y-axis, x is definitely equal to 0. And then y, we could say it starts off at y is equal to 2. Y is equal to 2. Maybe we'll say y is equal to 2 minus t. For t is between 0. T is greater than or equal to 0, less than or equal to 2. And that should work. When t is equal to 0, we're at this point right there. And then as t increases towards 2, we move down the y-axis until eventually, when t is equal to 2, we're at that point right there. So that's our parametrization. And so let's evaluate this line. And actually, we could do our derivatives too if we like. What's the derivative? Let me write right here. What's dx dt? Pretty straightforward. Derivative of 0 is 0. And dy dt is equal to the derivative of this is just minus 1, right? 2 minus t, derivative of minus t is just minus 1. And so let's just break it up. So we have this thing right here. So we have the integral along C2. But let's, instead of writing C2, I'll leave C2 there, but we'll say we're going from t is equal to 0 to 2 of f of xy. F of xy. So f of xy is this thing right here, is x plus y squared, and then times ds, times ds. And we know from the last several videos, ds can be rewritten as the square root of dx dt squared, so 0 squared, plus dy dt squared, so minus 1 squared is 1. All of that times dt. And obviously, this is pretty nice. It gets very nice and clean. This is 0 plus 1 square root. This just becomes 1. And then what is x? X, if we write it in terms of our parameterization, is always going to be equal to 0. And then y squared is going to be 2 minus t squared. So this is going to be 2 minus t squared. So this whole crazy thing simplified to, we're going to go from t is equal to 0 to t is equal to 2. The x disappears in our parameterization. X just stays 0 regardless of what t is. Of y, and then you have y squared, but y is the same thing as 2 minus t. So 2 minus t squared. And then you have your dt sitting out there. And this is pretty straightforward. I always find it easier to find when you're finding an antiderivative of this. Although you can do this in your head, I like to just actually multiply out this binomial. So this is going to be equal to the antiderivative from t is equal to 0 to t is equal to 2 of 4 minus 2 minus 4t plus t squared, just like that, dt. And then this is pretty straightforward. This is going to be, the antiderivative of this is 4t minus 2t squared, right? When you take the derivative, 2 times minus 2 is minus 4t. And then you have plus 1/3 t to the third, right? These are just simple antiderivatives, and we need to evaluate it from 0 to 2. And so let's evaluate it at 2. 4 times 2 is 8. Let me pick a new color. 4 times 2 is 8 minus 2 times 2 squared. So 2 times 4, so minus 8 plus 1/3 times 2 to the third power. So 1/3 times 8. So these cancel out. We have 8 minus 8. And we just have 8/3. So this just becomes 8/3. And then we have to put a 0 in, minus 0 evaluated here. But this is just going to be 0. We have 4 times 0, 2 times 0. All of these are going to be 0. So minus 0. So just like that, we found our surface area of our second wall. This turned out being, this right here is 8/3. And now we have our last wall. And then we can just add them up. So we have our last wall. We're looking, so let's just, I'll do another parameterization. I want to have the graph there. Well, maybe I can paste it again. Edit. So there's the graph again. And now we're going to do our last wall. So our last wall is this one right here, which is, we could write it, this was C3. Let me switch colors here. So this is C. We're going to go along contour C3 of f of xy ds, which is the same thing as, let's do a parameterization. Along this curve, if we just say x is equal to t, very straightforward, for t is greater than or equal to 0, less than or equal to 2. And then this whole time that we're along the x-axis, y is going to be equal to 0. That's a pretty straightforward parameterization. So this is going to be equal to, we're going to go from t is equal to 0 to t is equal to 2. T is equal to 2 of f of xy, which is, I'll write in terms of x right now, x and y, x plus y squared, times ds. Now, what is dx? Well, let me write ds right here, times ds. That's what we're dealing with. Now, we know what ds is. ds is equal to the square root of dx dt squared plus dy dt squared times dt. We proved that in the first video, or we didn't rigorously prove it, but we got the sense of why this is true. And what's the derivative of x with respect to t? Well, that's just 1. So this is just going to be a 1. 1 squared, same thing. And derivative of y with respect to t is 0. So this is a 0. 1 plus 0 is 1. Square root of 1 is 1. So this thing just becomes dt. ds is going to be equal to dt in this case. So this just becomes dt. And then our x is going to be equal to t. That's our definition of our parametrization. And y is 0, so we can ignore it. So this was a super simple integral. So this simplified down to, we're going to go from 0 to 2 of t dt, which is equal to, the antiderivative of t is just 1/2 t squared. And we're going to go 0 to 2, which is equal to 1/2 times 2 squared. 2 squared is 4, times 1/2 is 2. And then minus 1/2 times 0 squared, minus 0. So this third wall's area right there is just 2. Pretty straightforward. So that right there, the area there is just 2. And so to answer our question, what was this line integral evaluated over this closed path of f of xy? Well, we just add up these numbers. We have 4 plus 2 pi plus 8/3 plus 2. Well, what is this? 8/3 is the same thing as 2 and 2/3. So we have 4 plus 2 and 2/3 is 6 and 2/3, plus another 2 is 8 and 2/3. So this whole thing becomes 8 and 2/3, if you write it as a mixed number, plus 2 pi. And we're done. And we're done. Now we can start trying to do line integrals with vector valued functions. All of the work we've been doing so far with line integrals has been with scalar functions or scalar valued functions. And when I say that, that just means you give me an x and a y, and you evaluate the function at that x and y, and you get another scalar value. You get just a number. You don't get a vector. So what I want to do in this video is start to get ourselves warmed up with regards to vectors so that we can understand what it means to take a line integral with vector valued functions. So let me write down some vector valued functions. Actually, even a better place to start, let me draw a curve, or let me describe a curve. So let's put that little f of xy to the side. We can ignore it for now. But let's say I have some curve C, and it's described. It can be parameterized. I can't say that word. As, let's say, x is equal to x of t, y is equal to some function y of t. And let's say that this is valid for t is between a and b. So t is greater than or equal to a, and then less than or equal to b. So if I were to just draw this on a, let me say, I could draw it like this. I'm staying very abstract right now. This is not a very specific example. This is the x-axis. This is the y-axis. My curve, let's say this is when t is equal to a. And then the curve might do something like this. I don't know what it does. Let's say it's over there. This is t is equal to b. This actual point right here will be x of b. That would be the x coordinate. You evaluate this function at b, and y of b. And this is, of course, when t is equal to a. The actual coordinate in R2 on the Cartesian coordinates will be x of a, which is this right here, and then y of a, which is that right there. And we've seen that before. That's just a standard way of describing a parametric equation or curve using two parametric equations. What I want to do now is describe this same exact curve using a vector valued function. So if I define a vector valued function, and if you don't remember what those are, we'll have a little bit of a review here. Let me say I have a vector valued function r. And I'll put a little vector arrow on top of it. In a lot of textbooks, they'll just bold it, and they'll leave scalar valued functions unbolded. But it's hard to draw a bold, so I'll put a little vector on top. And let's say that r is a function of t. And these are going to be position vectors. Position vectors. Position vectors. And I'm specifying that because in general, when someone talks about a vector, this vector and this vector are considered equivalent as long as they have the same magnitude and direction. No one really cares about what their start and end points are, as long as their direction is the same and their length is the same. But when you talk about position vectors, you're saying, no, these vectors are all going to start at 0 at the origin. And when you say it's a position vector, you're implicitly saying this is specifying a unique position. In this case, it's going to be in 2-dimensional space, but it could be in 3-dimensional space, or really even 4, 5, whatever, n-dimensional space. So when you say it's a position vector, you're literally saying, OK, this vector literally specifies that point in space. So let's see if we can describe this curve as a vector, a position vector valued function. So we can say r of t, let me switch back to that pink color. I'll just stay in green, is equal to x of t times the unit vector in the x direction. The unit vector gets a little caret on top, a little hat. That's like the arrow for it. That just says it's a unit vector. Plus y of t times j. If I was dealing with a curve in 3 dimensions, I would have plus z of t times k. But we're dealing with 2 dimensions right here. And so the way this works is you're just taking your, well, for any t, and still we're going to have t is greater than or equal to a, and then less than or equal to b. And this is the exact same thing as that. Let me just redraw it. So let me draw our coordinates. Our coordinates right here, our axes. So that's the y-axis, and this is the x-axis. So when you evaluate r of a, right, that's our starting point. So let me do that. So r of a, maybe I'll do it right over here. Our position vector valued function evaluated at t is equal to a is going to be equal to x of a times our unit vector in the x direction plus y of a times our unit vector in the vertical direction, or in the y direction. And what's that going to look like? Well, x of a is this thing right here. So it's x of a times the unit vector. So it's really, maybe the unit vector is this long. It has length 1. So now we're just going to have a length of x of a in that direction. And then same thing in y of a. It's going to be y of a length in that direction. But the bottom line, this vector right here, if you add these scaled values of these 2 unit vectors, you're going to get r of a looking something like this. It's going to be a vector that looks something like that. Just like that. It's a vector. It's a position vector. That's why we're nailing it at the origin, but drawing it in standard position. And that right there is r of a. Now, what happens if a increases a little bit? What is r of a plus a little bit? And I don't know, we could call that r of a plus delta, or r of a plus h. We do it in different colors. So let's say we increase a little bit. R of a plus some small h. Well, that's just going to be x of a plus h times the unit vector I plus y times a plus h times the unit vector j. And what's that going to look like? Well, we're going to go a little bit further down the curve. That's like saying the coordinate x of a plus h and y plus a plus h. It might be that point right there. So it'll be a new unit vector. It'll be a new unit vector. Sorry, it'll be a new vector, position vector, not a unit vector. These don't necessarily have length 1. That might be right here. I'm going to do that same color as this. So it might be just like that. So that right here is r of a plus h. So you see, as you keep increasing your value of t until you get to b, these position vectors are going to keep specifying. We're going to keep specifying points along this curve. So the curve, let me draw the curve in a different color. The curve looks something like this. It's meant to look exactly like the curve that I have up here. And for example, r of b is going to be a vector that looks like this. It's going to be a vector that looks like that. I want to draw it relatively straight. That vector right there is r of b. So hopefully you realize that, look, these position vectors really are specifying the same points on this curve as this original, I guess, straight up parametrization that we did for this curve. And I just want to do that as a little bit of a review, because we're now going to break into the idea of actually taking a derivative of this vector valued function. And I'll do that in the next video.
Now look at this net that I just found. When I say go, be ready to throw. Go! Throw it at him, not me! Oh, let's try something else. Now watch and learn. Here's the deal. You slip and slide on this banana peel. What are you doing?
last video, we hopefully got ourselves a respectable understanding of how a vector-valued function works, or even better, a position vector-valued function that is in some ways a replacement for our traditional parametrization to describe a curve. And what I want to do in this video is just get a little bit of a gut sense of what it means to take of a derivative of a vector-valued function. In this case, it'll be with respect to our parameter t. So let me draw some new stuff right here. So let's say I have the vector-valued function r of t, and this is no different than what I did in the last video, x of t times unit vector I plus y of t times the unit vector j. If we're dealing in 3 dimensions, we'd add a z of t times k, but let's keep things relatively simple. And let's say that this describes a curve, and let's say the curve, let's say we're dealing with between t is between a and b, and this curve will look something like, let me do my best effort to draw the curve. Just draw some random curve here. So let's say the curve looks something like that. This is when t is equal to a, so it's going to go in this direction. This is when t is equal to b right here. This is t is equal to a, so this right here would be x of a. This right here is y of a. And similarly, this up here, this is x of b. And this over here is y of b. Now, we saw in the last video that the endpoints of these position vectors are what's describing this curve. So r of a, we saw in the last video, it describes that point right there. I don't want to review that too much. But what I want to do is think about what is the difference between 2 points. So let's say that we take some random point here. Let's say some random t here. Let's call that r of t. Let's say, well, actually, I'm going to do a different point just because I want to make it a little bit clearer. So let's say, I'm going to switch colors. Let's say that that right there is r of some t, some particular t right there. That is r of t. It's going to be, a plus something. So that's some particular t. And let's say that we want to figure out, and let's say we increase t by a little bit, by h. So let's say that r of t plus h, well, if we view the parameter t as time, we can kind of view we've moved forward in time by some amount. So our little particle has moved a little bit. And let's say that we're over here. So that is that right there. In yellow is r of t plus h, just a slightly larger value for h. Now, one question we might ask ourselves is how quickly is r changing with respect to t? So the first thing we might want to say was, what's the difference between these two? If I were to take, and I want to visualize it. If I were to take r, the position vector, that we get by evaluating r at t plus h, and from that I were to subtract r of t. R of t. What do we get? Well, you might want to review some of your vector algebra, but we're essentially just going to get this vector. Let me do it in a nice vibrant color. We're going to get this vector right there that I'm doing in magenta. So that magenta vector right there is, let me do it, that magenta one right there is the vector r of t plus h minus r of t. And it should make sense, because when you add vectors, you go heads to tails. You could alternatively write this as r of t plus this character right here, plus r of t plus h minus r of t. When you add 2 vectors, you're adding, let me make it very clear, I'm adding this vector to this vector right here. You put the tail of the second vector at the head of the first. So this is the first vector, and then I put the tail of the second there. And then the sum of those two, as we predicted, should be equal to this last one. It should be equal to r of t plus h. And we see that is the case. And even algebraically, you would see that obviously this guy and that guy are going to cancel out. So hopefully that satisfies you. And I want to be clear. This, all of a sudden, this isn't a position vector. We're not saying that, hey, let's nail this guy's tail at the origin and use this guy to describe a unique position. Now all of a sudden, it's just kind of a pure vector. It's describing just a change between 2 other position vector. So this guy is right out here. But this vector literally describes the change. But let's say we care, and how would this look algebraically if we were to expand it like that? So this is going to be equal to, what's r of t plus h? That's the same thing as x of, let me do it over here. This is the same thing as x of t plus h times the unit vector I plus y of t plus h times the unit vector j. That's just that piece. That piece right there is that piece minus, so this piece. So minus, I'll do it in the second line. I could have done it out here, but I'm running out of space. Minus x of t, right? R of t is just x of t times I plus, but I'll just distribute the minus sign. So it's minus y of t times j. Y. Actually, let me write it. This would be minus, let me write it this way, plus this. So you realize that this is really just this guy right here. I'm just evaluating at t. So you have x of t and y of t, and then later we can distribute, right? If you distribute this minus sign, you get a minus x of t and a minus y of t. And in vector addition, and this might be, you might need a little review on this if you haven't seen it in a while. You know that you can just add the corresponding components. You can add the x components and you can add the y components. So this is going to be equal to, let me rewrite it over here because I think I'm going to need some space later on. So let me rewrite it over here. So I have r of t plus h minus r of t is equal to, now I'm just going to group the x and the y components. This is equal to the x components added together, but this is a negative, so we're going to subtract this guy from that guy. So x of t plus h minus x of t, and then all of that times our unit vector in the x direction. And then we'll have plus y of t plus h minus y of t times the unit vector in the j direction. I'm just rearranging things right now. And this will tell us what is our change between any two r's for a given change in distance. And our change in distance here is h, between any two position vectors. Now, what I set out at the beginning of this video, I said, well, I want to figure out the change, and we're going to think about the instantaneous change with respect to t. So I want to see, well, how much did this change over a period of h? Over a period of h. We could have, instead of writing h, we could have written delta t. It would have been the same thing. So I want to divide this by h. So I want to say, look, my vector has changed this much, but I want to say it's over a period of h. And this is analogous to when we do slope. We say rise over run over delta y or change in y over change in x. This is kind of the change in our function per change in x. So let's just divide everything, or I shouldn't say change in x, per change in t. So here our change in t is h, right? The difference between t plus h and t is just going to be h. And so we're going to divide everything by h. When you multiply a vector by some scalar or divide it by some scalar, you're just taking each of its components and multiplying or dividing by that scalar. And we get that right there. So this, for any finite difference right here, h, this will tell us how much our vector changes per h. But if we want to find the instantaneous change, right, just like what we did when we first learned differential calculus, we said, OK, this is kind of analogous to a slope. This would be good. This would work out well for us if the path looked something like, if the path under question looked something like this. If it was a linear path, if our path looked something like this, we could just calculate this, and we'll essentially have the average change in our position vectors. So you can imagine two position vectors. That's one of them. Well, actually, they'd all be parallel. Well, they don't always. Well, the position vectors, they don't have to be parallel, but I won't. They don't have to be parallel. They could be like that. And then this would just describe the change between these two per h, or how quickly are the position vectors changing per our change in our parameter, right? The h you could also consider as kind of a delta t. Sometimes people find the h more simpler. Sometimes they find the delta t. But anyway, I'm concerned with the instantaneous. We're dealing with curves. We're dealing with calculus. This would have been OK if we were just in an algebraic linear world. So what do? Well, maybe we can just take the limit as h approaches 0. So let me scroll this over. So let's just take the limit. Let me do this in a nice vibrant color. Let's take, I'm running out of colors, the limit as h approaches 0 of both sides of this. So here too, I'm going to take the limit as h approaches 0. And here too, I'm going to take the limit as h approaches 0. So I just want to say, well, what happens? How much do I change per a change in my parameter t? But what's kind of the instantaneous change as the difference gets smaller and smaller and smaller? This is exactly what we first learned when we learned about instantaneous slope or instantaneous velocity or slope of a tangent line. Well, this thing looks a little bit undefined to me right now. We haven't defined limits for vector valued functions. We haven't defined derivatives for vector valued functions. But lucky for us, all of this stuff here looks pretty familiar. This is actually the definition of our derivative. And these are scalar valued functions right here. They're multiplied by vectors in order for us to get vector valued functions. But this right here, by definition, this is the derivative. This is x prime of t. Or this is dx dt. This right here is y prime of t. Or we could write that as dy dt. So all of a sudden we can define, we can say, and I'm being a little hand wavy here, but I want to give you the intuition more than anything. We can say that the derivative, we can call this expression right here as the derivative of my vector valued function r with respect to t. Or we could call it dr dt. Notice I keep the vector signs there. This is this derivative, and all it's going to be equal to, r prime of t is going to be equal to, well, this is just the derivative of x with respect to t is equal to x prime of t times the x unit vector, the horizontal unit vector, plus y prime of t times the y unit vector times j, the unit vector in the horizontal direction. That's a pretty nice and simple outcome. But the harder thing, maybe, is to kind of visualize what it represents. So if we think about what happens, let me draw a big graph just to get the visualization going in a healthy way. So let's say my curve looks something like this. That's my curve. And let's say that this is, we want to figure out the instantaneous change at this point right here. So that is r of t. And then if we take r of t plus h, we saw this already. You know, t plus h might be something like right there. So this is r of t plus h. Now, right now, the difference between these two, and this is just the numerator when you take the difference, or how fast we're changing, from this vector to that vector in terms of t. And it's hard to visualize here. And I'm going to do a whole video so we can think about the magnitude here. That might be that vector. Well, the difference between these two is just going to be that. But then when you divide it by h, it's going to be a larger vector. Right? If we assume h is a small number, let's say h is less than 1, we're going to get a larger vector, right? But this is kind of the average change over this time. But as h gets smaller and smaller and smaller, this r prime of t its direction is going to be tangential to the curve. And I think you can visualize that, right? As these two guys get closer and closer and closer and closer, the dr's get smaller. So the change, the dr, the difference between the two, the delta r's get smaller and smaller. You can imagine if h was even smaller, if it was right here, then all of a sudden the difference between those two vectors is getting smaller. And it's getting more and more tangential to the curve. It's getting more and more tangential to the curve. But then we're also dividing by a smaller h. So the actual derivative, as the limit as h approaches 0, it might be, maybe it's even a bigger number there. And actually, the magnitude of this vector, it's a little hard to visualize. It's going to be dependent on a parametrization for the curve. It's not dependent on the shape of the curve. The direction of this vector is dependent on the shape of this curve. And the direction, this will be tangent to the curve. Or you could imagine that this vector is on the tangent line to the curve. The magnitude of it is a little bit harder to understand. I'll try to give you a little bit of intuition on that in the next video. But this is what I want you to understand right now, because we're going to be able to use this in the future when we do the line integral over vector valued functions. last couple of videos, we saw that we can describe a curve by a position vector valued function. And in very general terms, it would be the x position as a function of time times the unit vector in the horizontal direction, plus the y position as a function of time times the unit vector in the vertical direction. And this will essentially describe this, if you can imagine a particle, and let's say the parameter t represents time, it'll describe where the particle is at any given time. And if we wanted a particular curve, we can say, well, this only applies for, let's say for some curve, we're dealing, it's r of t, and it's only applicable between t being greater than a and less than b. And that would describe some curve in 2 dimensions. Let me just draw it here. This is all a review of really the last 2 videos. So this curve, it might look something like that, where this is where t is equal to a, that's where t is equal to b. And when, so r of a will be this vector right here that ends at that point, and then as t, or if you can imagine the parameter being time, it doesn't have to be time, but that's a convenient one to visualize. Each corresponding as t gets larger and larger, we're just going to we're specifying different points on the path. We saw that 2 videos ago. And in the last video, we thought about, well, what does it mean to take the derivative of a vector valued function? And we came up with this idea that, and it wasn't an idea, we actually showed it to be true. We came up with a definition, really, that the derivative, I could call it r prime of t, and it's going to be a vector. The derivative of a vector valued function is once again going to be a derivative, but it was equal to, the way we defined it, x prime of t times I plus y prime of t times j. Or another way to write that, and I'll just write all the different ways just so you get familiar with, dr dt is equal to dx dt. This is just a standard derivative. X of t is a scalar function. So this is a standard derivative times I plus dy dt times j. And if we wanted to think about the differential, one thing that we can think about, and whenever I do the math with the differential, it's a little bit hand wavy. I'm not being very rigorous, but if you imagine multiplying both sides of this equation by a very small dt, or this exact dt, you would get dr is equal to, I'll just leave it like this, dx dt times dt. I could make these cancel out, but I'll just write it like this first, times the unit vector I plus dy dt times the unit times dt times the unit vector j. Or we could rewrite this, and I'm just rewriting it in all of the different ways that one can rewrite it. You could also write this as dr is equal to x prime of t dt times the unit vector I. Sorry, this was x prime of t dt, right? This is x prime of t right there, times the unit vector I, plus y prime of t, that's just that right there, times dt times the unit vector j. And just to, I guess, complete the trifecta, the other way that we could write this is that dr is equal to, if we just allowed these to cancel out, then we get is equal to dx times I plus dy times dy times j. And that actually makes a lot of intuitive sense, that if I look at any dr, so let's say I look at the change between this vector and this vector, let's say the super small change right there, that is our dr. And it's made up of, it's our dx, our change in x, is that right there. You could imagine it's that right there, times, but we're vectorizing it by multiplying it by the unit vector in the horizontal direction, plus dy times the unit vector in the vertical direction. So when you multiply this distance times the unit vector, you're essentially getting this vector. You're essentially getting this vector right here. And when you multiply this guy, and actually our change in y here is negative, you're going to get this vector right here. So when you add those together, you get your change in your actual position vector. So that was all a little bit of background, and this might be somewhat useful in a future video from now. Actually, I'm gonna leave it there because I just wanted to introduce this notation and get you familiar with it. In the next video, what I'm going to do is give you a little bit more intuition for what exactly what exactly does this thing mean? And how does it change depending on different parametrizations? And I'll do it with two different parametrizations for the same curve. What I want to do in this video is to make two parametrizations of essentially the same curve, but we're going to go along the curve at different rates. And hopefully we'll be able to use that to understand or get a better intuition behind what exactly it means to take a derivative of a position vector valued function. So let's say my first parameterization, I have x of t is equal to t. And let's say that y of t is equal to t squared. And this is true for t is greater than or equal to 0 and less than or equal to 2. And if I want to write this as a position vector valued function, let me write this x1, let me call that y1, and let me write my position vector valued function. I could say r1, because I'm numbering them because I'm going to do a different version of this exact same curve with a slightly different parameterization. So r1 of t, we could say, is x1 of t times I, the unit vector I. So we'll just say t times I plus, right, this is just x of t right here, or x1 of t. I'm numbering them because I'll later have an x2 of t, plus t squared times j. And if I wanted to graph this, I'm going to be very careful graphing it because I really want to understand what the derivative means here. So let me get my draw. Let me try to draw it roughly to scale. So let's say that this is, so we got 1, 2, 3, 4. And then let me draw my x-axis. That's good enough. And my x-axis, I want it to be roughly to scale 1 and 2. And so at t equals 0, both my x and y coordinates are at 0, or this is just going to be the 0 vector. So this is where we are at t equals 0. At t equals 1, this is going to be 1 times I, so we're going to be just like that, plus 1 times j, right? 1 squared is j, so we're going to be right there. And then at t is equal to 2, we're going to be at 2i. So 2i, you can imagine 2 times I would be this vector right there. Right? 2 times I plus 4, right? 2 squared is 4. 4 times j. So plus this plus 4 times j, right? That's 4 times j. If you add these two vectors, heads to tails, you're going to get a vector that goes, that endpoint is right there. The vector is going to look something like this. I don't want to. So this is what, just to make it clear what we're doing, that's r1 of 2. Right? This is r1 of 0. This is r1 of 1. But the bottom line is the path looks like this. It's a parabola. So the path will look like that. Just like that. Now, that's in my first parameterization of it. Actually, let me draw it a little bit more carefully. And I want to get rid of this arrows just because I want it to be a nice, clean drawing. So it's going to be a parabola. Well, that's not as. Actually, let me get rid of that other point too, just because I didn't draw it exactly where it needs to be. It needs to be right there. And my parabola, or my part of my parabola, is going to look something like that. All right, good enough. So this is the first parameterization. Now I'm going to do this exact same curve, but I'm going to do it slightly differently. So let's say I'll do it in different colors. So x2 of t, let's say it equals 2t. And y2 of t, let's say it's equal to 2t squared. Or we could alternatively write that. That's the same thing as 4t squared, just raising both of these guys to the second power. That's equal to 4t squared. I could write it either way. And then let's say my second parameterization, and let's say instead of going from t equals 0 to 2, we're going to go from t goes from 0 to 1. T goes from 0 to 1. But we're going to see we're going to cover the exact same path. And our second vector or position vector valued function, r2 of t, is going to be equal to 2t times I plus, I could say 2t squared or 4t squared times j. And if I were to graph this guy right here, it will look like, I'll draw my axes again. It's going to look the same, but it's, I think, useful to draw it because I'm going to draw the derivatives and all of that on it later. So let's see, 1, 2, 3, 4, 1, 2. And then let's see what happens. When t is equal to 0, when t is equal to 0, or r of 0, all of these are going to be 0. We're just going to get the 0 vector. X and y are both equal to 0. When t is equal to 1/2, so when t is equal to 1/2, what are we going to get here? 1/2 times 2 is 1. And then we're going to get the point 1/2 squared is 1/4 times 4 is 1. So when t is equal to 1/2, we're going to be at the point 1, 1. And when t is equal to 1, we're going to be at the point 2, 4. Right? 2, 4. So notice the curve is exactly, the path we go is exactly the same. But before we even do the derivatives, these two paths are identical. I want to think about something. Let's pretend that our parameter t really is time, that t is equal to time. And that tends to be the most common, that's why they call it t. It doesn't have to be time, but let's say it is time. So what's happening here? In this first parametrization, when we go from 0 to 2 seconds, we cover this path, right? You can imagine after 1 second, the dot moves here, then it moves there. You can imagine a dot moving along this curve, and it takes 2 seconds to do so. In this situation, we have a dot moving along the same curve, but it's able to cover the same curve in only 1 second. In half a second, it gets here. It took this guy 1 second to get here. In 1 second, this guy's all the way over here. This guy takes 2 seconds to go over here. So in this second parametrization, even though the path is the same, the curves are the same, the dot is faster. Dot is faster. And I want you to keep that in mind when we think about the derivatives of both of these position vector valued functions. So just remember, the dot is moving faster. For every second, it's getting further along the curve than here. That's why it only took them 1 second. Now let's look at the derivatives of both of these guys. So the derivative here, so if I were to write r prime, r1 prime of t. Let me do it in a different color, actually. I already used the orange. So let me do it in a blue. r1 prime of t. So this is the derivative now is going to be, remember, it's just the derivative of each of these times the unit vectors. So the derivative of t with respect to t, that's just 1. So it's 1 times I. So I'll just write 1 I plus, I didn't have to write the 1 there, plus the derivative of t squared with respect to t is 2t plus 2tj. And let me take the derivative over here. r2 prime of t. The derivative of 2t with respect to t is 2, so 2i plus the derivative of 4t squared is 8t. Right? 2 times 4, it is 8t. 8t, just like that. Just like that. Now, the question is, what do their respective derivative vectors look like at different points? So let's look at, I don't know, let's see how fast they're moving when time is equal to 1. So let's take it at a specific point. This is just the general formula, but let's figure out what the derivative is at a specific point. So let's take r1 when time is equal to 1. And I want to take the specific point on the curve, not the specific point in time. So this point on the curve here is when time is equal to 1, you could say, second. This point over here, which is the exact corresponding point, is when time is equal to 1/2 second. So r1 of 1 is equal to, and we're taking the derivative there, is equal to 1i, right? It's not dependent on t at all. So it's 1i plus 2 times 1j, so plus 2j. So at this point, the derivative of our position vector function is going to be 1i plus 2j. So we can draw it like this. So if we do 1i is like this, 1i, and then 2j. Just 2j is like that. So our derivative right there, I'll do it in the same color that I wrote it in, is in this green color, is going to look like this. It's going to look like that. And notice, it looks like, at least its direction is, let me do it a little bit straighter. Its direction, that's not even, its direction looks tangent to the curve. It's going in the direction that my particle is moving. Remember, my particle is going from here to there, so it's going in the direction. And I'm going to think about in a second what this length of this derivative vector is. This right here, just to be clear, is r1 prime. It's a vector. So it's telling us the instantaneous change in our position vector with respect to t, or time, when time is equal to 1 second. That's this thing right here. Now, let's take the exact same position here on our curve, but that's going to occur at a different time for this guy. We already said it only takes him, he's here at time is equal to 1/2 second. So let's take, let me do it in, well, I can do it in the same color. So here we have R2. We're going to evaluate it at 1/2, because this is at time is equal to 1/2 seconds. And this is going to be equal to 2i. This isn't dependent at all on time. So 2i plus 8 times the time. So we're 8 time right here is 1/2. So 8 times 1/2 is 4. So plus 4j. So what does this look like? The instantaneous derivative here. Oh, and this is the derivative. I have to be very clear. So 2i, that's, let me draw some more. So 2i maybe gets us about that far, plus 4j will get us up to right around there. Plus 4j is that vector. So when you add those two heads to tails, you get this thing. You get something that, let me do it like, you get something that looks like that. Something that looks like that. I didn't draw it as neatly as I would like to. But let's notice something. Both of these vectors are going in the exact same direction. They're both tangential to the path, to our curve. But this vector is going, its length, its magnitude is much larger than this vector's magnitude. And that makes sense, because I hinted at it when we first talked about these vector valued position functions and their derivatives, is that the length, you can kind of view it as the speed. The length is equal to the speed. If you imagine time, t being time, and these parametrizations are representing a dot moving along these curves. So in this case, the particle only takes a second to go there. So at this point in its path, it's moving much faster than this particle is. So if you think about it, this vector right here, if you imagine this is a position vector, this is velocity. This right here is velocity. Right? Velocity is speed plus direction. Speed is just, how fast are you going? Velocity is how fast you're going in what direction. I'm going this fast in, and you could calculate it using Pythagorean theorem, but I just want to give you the intuition right here. I'm going that fast in this direction. Here I'm going this fast. I'm going even faster. That's my magnitude, but I'm still going in the same direction. So hopefully you have a gut feeling now of what the derivative of these position vectors really are. One of the most fundamental ideas in all of physics is the idea of work. And when you first learn work, you just say, oh, that's just force times distance. But then later on, when you learn a little bit about vectors, you realize that the force isn't always going in the same direction as your displacement. So you learn that its work is really the magnitude. Let me write this. The magnitude of the force. Magnitude of force of the force in the direction, or the component of the force in the direction of displacement. Displacement is just distance with some direction. In direction of displacement times the magnitude of the displacement. Or you could just kind of say times the distance displaced. Times the distance. I'm not being too particular about it. And the classic example, maybe you have an ice cube or some type of block. I just say ice so that it's not a lot of friction. Maybe it's standing on a bigger sheet, a lake or ice of something. And maybe you're pulling on that ice cube at an angle. Let's say you're pulling at an angle like that. That is my force right there. Let's say my force is equal to, well, that's my force vector. Let's say the magnitude of my force vector. So I'll say the magnitude, sometimes we put 2 brackets around there. The magnitude of my force vector, we can say is, let's say it's 10 newtons. And let's say the direction of my force vector, right? Any vector has to have a magnitude and a direction. And the direction, let's say it has a 30-degree angle. Let's say it's 60-degree angle above horizontal. So that's the direction I'm pulling in. And let's say I displace it. let's say I display, and this is all a bit of review, hopefully. If you're displacing it, let's say you displace it 5 newtons. So let's say the displacement, that's the displacement vector right there, and the magnitude of it is equal to 5, sorry, not 5 newton, 5 meters. So you've learned from the definition of work, you can't just say, oh, I'm pulling with 10 newtons of force and I'm moving it 5 meters. You can't just multiply the 10 newtons times the 5 meters. You have to find the magnitude of the component going in the same direction as my displacement. So what I essentially need to do is the length, if you imagine the length of this vector being 10, that's the total force, but you need to figure out the length of the vector that's the component of the force going in the same direction as my displacement. And a little simple trigonometry, you know that this is 10 times the cosine of 60 degrees. 10 times the cosine of 60 degrees, or that's equal to, cosine of 60 degrees is 1/2, so that's just equal to 5. So this magnitude, the magnitude of the force going in the same direction of the displacement in this case, is 5 newtons. 5 newtons. And then you can figure out the work. You could say that the work is equal to 5 newtons times, I'll just write a dot for times. I don't want you to think it's cross product, times 5 meters, which is 25 newton meters, or you could even say 25 joules of work have been done. And this is all, really a review of somewhat basic physics. But just think about what happened here. What was the work? If I wrote it right in the abstract, the work is equal to the 5 newtons. That was the magnitude of my force vector. So it's the magnitude of my force vector times the cosine of this angle, times the cosine of the, so let's call that theta. Let's say it a little generally. So times the cosine of the angle. This is the amount of my force in the direction of the displacement, the cosine of the angle between them, times the magnitude of the displacement. So times the magnitude of the displacement. Or if I wanted to rewrite that, I could just write that as the magnitude of the displacement times the magnitude of the force times the cosine of theta. And I've done multiple videos of this in the linear algebra playlist and the physics playlist, where I talk about the dot product and the cross product and all of that. But this is the dot product. This is the dot product of D and F, of the vectors D and F. So in general, if you're trying to find the work for a constant displacement and you have a constant force, you just take the dot product of those two vectors. And if the dot product is a completely foreign concept to you, you might want to watch, I think I've made multiple, 4 or 5 videos on the dot product and its intuition and how it compares. But just to give you a little bit of that intuition right here, the dot product, when I take F dot D, or D dot F, what it's giving me is I'm multiplying the magnitude. Well, I could just read this out. But the idea of the dot product is take how much of this vector is going in the same direction as this vector, and in this case it's this much, and then multiply the two magnitudes. And that's what we did right here. So the work is going to be the force vector dot, taking the dot product of the force vector with the displacement vector. And this, of course, is a scalar value. And we'll work out some examples in the future where you'll see that that's true. So this is all a review of fairly elementary physics. Now let's take a more complex example, but it's really the same idea. Let's define a vector field. Let's define a vector field. So let's say that I have a vector field F, and we're going to think about what this means in a second. It's a function of x and y, and it's equal to some scalar function of x and y times the I unit vector, or the horizontal unit vector, plus some other function, scalar function of x and y, times the vertical unit vector. So what would something like this be? This is a vector field. This is a vector field in two-dimensional space, or on the xy plane. This is a vector field on xy plane. Or you could even say on R2. Either way, I don't want to get too much into the mathiness of it. But what does this do? Well, if I were to draw my xy plane, so that is my, again, I'm having trouble drawing a straight line. All right, there we go. That's my y-axis, and that's my x-axis. I'm just drawing the first quadrant, but you could go negative in either direction if you like. What does this thing do? Well, it's essentially saying, look, you give me any x, any y. You give any xy in the xy plane, and these are going to end up with some numbers, right? These are going to, when you put xy here, you're going to get some value. And when you put xy here, you're going to get some value. So you're going to get some combination of the I and j unit vector. So you're going to get some vector. So what this does is defines a vector that's associated with every point on the xy plane. So you could say, hey, if I take this point on the xy plane, and I were to pop it into this, I'll get, something times I plus something times j. And when you add those two, maybe I get a vector that looks like something like that. Maybe, and you can do it on every point. I'm just taking random samples. Maybe when I go here, the vector looks something like that. Maybe when I go here, the vector looks like this. Maybe when I go here, the vector looks like that. Maybe when I go up here, the vector goes like that. I'm just randomly picking points. It defines a vector on all of the xy coordinates where these functions, these scalar functions, are properly defined. And that's why it's called a vector field. It defines what a potential maybe force would be, or some other type of well, we could say force at any point. At any point, if you happen to have something there, maybe that's what the function is. And I could keep doing this forever and filling in all the gaps, but I think you get the idea. It associates a vector with every point on the xy plane. Now, this is called a vector field, so it probably makes a lot of sense that this could be used to describe any type of field. It could be a gravitation field. It could be an electric field. It could be a magnetic field. And this could be essentially telling you how much force there would be on some particle in that field. That's exactly what this would describe. Now, let's say that in this field, I have some particle traveling on the xy plane. And let's say it starts here. Let's say it starts there, and by virtue of all of these crazy forces that are acting on it, and maybe it's on some tracks or something, so it won't always move exactly in the direction that the field is trying to move it at. So let's say it moves in a path that moves something like this, and let's say that this path or this curve is defined by a position vector function. So let's say that that's defined by r of t, which is just x of t times I plus y of t times our unit vector j. That's r of t right there. Well, in order for this to be a finite path, this is true before t is greater than or equal to a and less than or equal to b. This is the path that the particle just happens to take due to all of these wacky forces. So when the particle is right here, maybe the vector field acting on it, maybe it's putting a force like that. But since the thing is on some type of tracks, it moves in this direction. And then when it's here, maybe the vector field is like that, but it moves in that direction because it's on some type of tracks. Now, everything I've done in this video is to build up to a fundamental question. What was the work done on the particle by the field? Work done on the particle. What was the work done on the particle by the field? To answer that question, we could zoom in a little bit. Let's say we go to, I'm going to zoom in on only, a little small snippet of our path. And let's just try to figure out what the work is done in a very small part of our path, because it's constantly changing. The field is changing directions. My object is changing direction. So let's say when I'm here, and let's say I move a small amount of my path. So let's say I move, this is an infinitesimally small dr, right? I have a differential. It's a differential vector, infinitely small displacement. And let's say over the course of that, I had the vector field is acting in this local area. Let's say it looks something like that. It's providing a force that looks something like that. So that's the vector field in that area, or the force directed on that particle right when it's at that point, right? There's an infinitesimally small amount of time and space. So you could say, okay, over that little small point, we have this constant force. What was the work done over this small period? You could say, what's this small interval of work? You could say d work, or a differential of work. Well, by the same exact logic that we did with the simple problem, it's the magnitude of the force in the direction of our displacement times the magnitude of our displacement. And we know what that is just from the this example up here, that's the dot product. It's the dot product of the force and our super small displacement. So that's equal to the dot product of our force and our super small displacement. Now, just by doing this, we're just figuring out the work over maybe like a really small, super small dr. But what we want to do is we want to sum them all up. We want to sum up all of the dr's to figure out the total, all of the f dot dr's to figure out the total work done. And that's where the integral comes in. We will do a line integral over, I mean, you could think of it two ways. You could write just dw there, but we could say we'll do a line integral that says along this curve C, we could call that C, or along R, whatever you want to say it, of dw. That'll give us the total work. So let's say work is equal to that. Or we could also write it over the integral, over the same curve of f dot dr. And this might seem like a really, gee, this is really abstract, Sal. How do we actually calculate something like this? Especially because we have everything parametrized in terms of t. How do we get this in terms of t? And if you just think about it, what is f dot r, or what is f dot dr? Well, actually, to answer that, let's remember what dr looked like. If you remember dr dt is equal to x prime of t. I'm writing it like I could have written dx dt if I wanted to, times the I unit vector, plus y prime of t times the j unit vector. And if we just wanted dr, we could multiply both sides if we're being a little bit maybe more hand wavy with the differentials, not too rigorous. We'll get dr is equal to x prime of t dt times the unit vector I, plus y prime of t times the differential dt times the unit vector j. So this is our dr right here. That is our dr. And remember what our force, our vector field was. It was this thing up here. Let me copy and paste it. And then we'll see that the dot product is actually not so crazy. So I'm going to copy, and then let me paste it down here. All right. I'll paste it down there. So what's this integral going to look like? This integral right here that seems, gives us the total work done by the field on the particle as it moves along that path, which is super fundamental to pretty much any serious physics that you might eventually find yourself doing. So you could say, well, gee, it's going to be the integral. Well, let's just say from t is equal to a to t is equal to b, right? A is where we started off on the path. T is equal to a to t is equal to b. You could imagine it as being time, as a particle moving as time increases. And then what is f dot dr? What is f dot dr? Well, if you remember from just what the dot product is, you can essentially just take the product of the corresponding components of your vector and add them up. So this is going to be the integral from t equals a to t equals b of p of x. Really, instead of writing xy, is x of t, right? X is a function of t. Y is a function of t. So that's that. Times this thing right here, times this component, right? We're multiplying the I components. So times x prime of t dt. And then that plus, we're going to do the same thing with the q function. So this is q plus, I'll go to another line. Hopefully you realize I could have just kept writing, but I'm running out of space. Plus q of x of t, y of t, times the component of our dr, times the y component, or the j component, y prime of t dt. And we're done. And we're done. This might still seem a little bit abstract, but we're going to see in the next video that this is actually, everything is now in terms of t. So this is just a straight up integration with respect to dt. If we want, we could take the dt's outside of the equation, and it'll look a little bit more normal for you. But this is essentially all that we have to do. And we're going to see some concrete examples of taking a line integral through a vector field, or using vector functions in the next video.
We are number
let's apply what we learned in the last video and do a concrete example of the work done by a vector field on something going through some type of path through the field. So let's say that I have a vector field. It's defined over R2 over the xy plane. So it's a function of x and y. It associates a vector with every point on the plane. And let's say my vector field is y times the unit vector I. Let's say minus x times the unit vector j. And so you can imagine if we were to draw, let's draw our x and y axes. I'll do it over here. If we were to draw our x and y axes, this associates a vector, a force vector. Let's say this is actually a force vector with every point in our xy plane. So this is x and this is y. So if we're at the point, for example, 1, 0, what will the vector look like that's associated with that point? Well, at 1, 0, y is 0. So this will be 0i minus 1j. Minus 1j looks like this. So minus 1j will look like that. At x is equal to 2, I'm just picking points at random, ones that'll be easy. Y is still 0, and now the force vector here would be minus 2j. So it would look something like this. Minus 2j. Something like that. Likewise, if we were to go here where y is equal to 1 and x is equal to 0, when y is equal to 1, we have 1i plus minus 0j. So then our vector is going to look like that at this point. Our vector will look like that. And if we were to go to 2, you can get the picture. You can keep plotting these points. You just want to get a sense of what it looks like. If you go here, the vector is going to look like that. If you go maybe this point right here, the vector is going to look like that. I think you get the general idea. I could keep filling in the space for this entire field all over, just to make it symmetric. If I was here, if I was right over here, the vector is going to look like that. You get the idea. I could just fill in all of the points if I had to. Now, in that field, I have some particle moving. And let's say its path is described by the curve C. And the parametrization of it is x of t is equal to cosine of t. And y of t is equal to sine of t. And the path will occur from t, let's say 0 is less than or equal to t, is less than or equal to 2 pi. You might already recognize what this would be. This parameterization is essentially a counterclockwise circle. So the path that this guy is going to go is going to start here, where you can imagine t in this case, you can almost, you can imagine it's the angle of the circle, but you could also imagine t is time. So time equals 0, we're going to be over here. Then at time of pi over 2, we're going to have traveled. We're going to have traveled quarter of the circle to there. So we're moving in that direction. And then at time, after pi seconds, we would have gotten right there. And then all the way after 2 pi seconds, we would have gotten all the way around the circle. So we're doing our path, our curve, is one counterclockwise rotation around the circle, so to speak. So what is the work done by this field on this curve? So the work we learned in the previous video is equal to the line integral over this contour of our field, of our vector field, dotted with the differential of our movement. So dotted with the differential of our movement, dr. Well, I haven't even defined r yet. I mean, I kind of have just the parametrization here. So we need to have a vector function. We need to have some r that defines this path. This is just a standard parametrization. But if I wanted to write it as a vector function of t, we would write that r of t is equal to x of t, which is cosine of t, times I, plus y of t times j, which is just sine of t times j. And likewise, this is for 0 is less than or equal to t, which is less than or equal to 2 pi. This and this are equivalent. The reason why I took the pain of doing this is so now I can take its vector function derivative and I can figure out its differential, and then I can actually take the dot product with this thing over here. So let's do all of that and actually calculate this line integral and figure out the work done by this field. And one thing might already pop in your mind. We're going in a counterclockwise direction, but at every point where we're passing through, it looks like the field is going exactly opposite the direction of our motion. For example, here we're moving upwards, the field is pulling us backwards. Here we're moving to the top left, the field is moving us to the bottom right. Here we're moving exactly to the left, the field is pulling us to the right. So it looks like the field is always doing the exact opposite of what we're trying to do. It's hindering our ability to move. So I'll give you a little intuition. This will probably deal with negative work. For example, if I lift something off the ground, I have to apply force to fight gravity. I'm doing positive work, but gravity is doing negative work on that. But we're just going to do the math here just to make you comfortable with this idea. But it's interesting to think about what's exactly going here. Even here, the field is, the field I'm doing in that pink color, so let me stick to that. The field is pushing in that direction. So it's always going opposite the motion. But let's just do the math to make everything in the last video a little bit more concrete. So a good place to start is the derivative of our position vector function with respect to t. So let me switch. So we have dr dt, which we could also write as r prime of t. This is equal to the derivative of x of t with respect to t, which is minus sine of t times I, plus the derivative of y of t with respect to t. That's derivative of sine of t is just cosine of t times j. And if we want the differential, we just multiply everything times dt. So we get dr is equal to, we could write it this way. We could actually even just put the d, well, let me just do it. So it's minus sine of t dt. I'm just multiplying each of these terms by dt, distributive property, times the unit vector I, plus cosine of t dt times the unit vector j. So we have this piece now. And then we want to take the dot product with this over here. But let me rewrite our vector field in terms of t, so to speak. So what's our field going to be doing at any point t? We don't have to worry about every point. We don't have to worry, for example, that over here the vector field is going to be doing something like that, because that's not on our path. That force never had an impact on the particle. We only care about what happens along our path. So we can find a function that what we can essentially substitute y and x for their relative functions with respect to t, and then we'll have the force from the field at any point or any time t. So let's do that. So this guy right here, if I were to write it as a function of t, this is going to be equal to y of t, right? Y is a function of t. So it's sine of t, right? That's that. Sine of t times I, plus, or actually minus x, or x of t. X is a function of t. So minus cosine of t times j. And now all of it seems a little bit more straightforward. If we want to find this line integral is going to be the same thing as the integral. Let me pick a nice soothing color. Maybe this is a nice one. The integral from t is equal to 0 to t is equal to 2 pi of f dot dr, Now, when you take the dot product, you just multiply the corresponding components and add it up. So we take the product of the minus sign and the sine of t, or the sine of t with the minus sine of t dt, you're going to get minus sine squared t dt. And then you're going to add that to, so you're going to have that plus, let me write that dt a little bit. That was a wacky looking dt. And then you're going to have that plus these two guys multiplied by each other. So that's, well, there's a minus sign here. So plus, let me just change this to minus cosine squared dt. And if we factor out a minus sign and a dt, what is this going to be equal to? This is going to be equal to the integral from 0 to 2 pi of, we could say, sine squared plus, I want to put the t there, sine squared of t plus cosine squared of t. And actually, let me take the minus sign out to the front. So if we just factor the minus sign, so we put a minus there, make this a plus, make this a plus. So the minus sign out there, and we factor dt out. I did a couple of steps in there, but I think you got it. This is just algebra at this point. Factoring out a minus sign, so this becomes positive, and then you have a dt and a dt. Factor that out, and you get this. You could multiply this out, and you'll get what we originally have, if that confuses you at all. And the reason why I did that, we know what sine squared of anything plus cosine squared of that same anything is. That falls right out of the unit circle definition of our trig function. So this is just 1. So our whole integral has been reduced to the minus integral from 0 to 2 pi of dt. And this is, we've seen this before. We can say this is of 1 if you want to put something there. Then the antiderivative of 1 is just, so this is just going to be equal to minus, and that minus sign is just the same minus sign that we're carrying forward. The antiderivative of 1 is just t, and we're going to evaluate it from 2 pi to 0, or from 0 to 2 pi. So this is equal to minus, that minus sign right there, 2 pi minus t at 0, so minus 0. So this is just equal to minus 2 pi. And there you have it. We figured out the work that this field did on the particle, or whatever, as the whatever thing was moving around in this counterclockwise fashion. And our intuition held up. We actually got a negative number for the work done. And that's because at all times the field was actually going exactly opposite, or was actually opposing the movement of, if we think of it as a particle in its counterclockwise direction. Anyway, hopefully you found that helpful.